reflection and refraction. Light. There are variety of objects around us. However, it is due to the presence of light that we are able to see these objects around. Light is a form of energy which causes a sensation of vision and enables us to see various objects around us. Let us perform an activity to clear this concept.
Stand in front of a large mirror in a well-illuminated room. Can you see your image? Yes, you can see your image. Now, close all doors and windows of the room. Also switch off the light in the room. Can you see your image now? No, you cannot see your image. This shows that the presence of light is necessary to view an image because the light rays reflected from an object fall on the mirror and its image is formed. We are able to see an object when the incident light rays reflected from that object enters our eyes and its image is formed on the retina of our eyes. It is because of the presence of light that we can see the world around us. We can see the colorful rainbows, green forests, blue sky, colorful flowers, twinkling stars, and different objects in the surroundings in the presence of light. Let us understand the nature of light. Nature of light. Light is a form of energy called electromagnetic radiation which causes sensation of vision. Electromagnetic radiation spectrum includes X-rays, ultraviolet radiations, visible light, heat radiations, and radio waves, etc. Not all these parts of electromagnetic spectrum can be seen by our eyes. The part of the spectrum that we can see with our eyes is termed as visible light.
Do you know that light has a tendency to bend when an object of very small size, comparable to the wavelength of the light, comes on its way? This property of light is known as diffraction of light. Diffraction of light cannot be explained by straight line treatment of light rays. To explain this phenomenon, we need to consider light as a wave. But the wave theory of light fails to explain certain other properties of light, such as photoelectric effect. Thus, we can explain some properties of light by considering it as a wave and some others by considering it as a stream of particles. This confusion about the true nature of light was resolved when a modern quantum theory of light emerged. According to this theory, light has dual nature. It can behave like a wave or as a stream of particles. Till now, this theory is the most successful theory to explain the nature of light. Let us study some of the optical phenomena occurring in nature by understanding the reflection and refraction of light using the straight line propagation of light. Reflection of light. When the rays of light falls on a polished surface such as a mirror, they are reflected. The reflection of light follows certain laws known as laws of reflection. The laws of reflection are: the angle of incidence is always equal to the angle of reflection. That is, angle I is equal to angle R. The incident ray, the reflected ray, and the normal all lie in the same plane at the point of incidence. The incident ray and the reflected ray are on the opposite sides of the normal. These laws are applicable to all types of reflecting surfaces, including rough surfaces and spherical surfaces. You might have seen your image in a plane mirror. What are the characteristics of image formed by a plane mirror? Well, the image formed by a plane mirror is always virtual and erect. The size of the image is equal to that of the object. The image formed is as far behind the mirror as the object is in front of it. The image is laterally inverted. What would happen to the characteristics of the image if we replace the plane mirror by a curved mirror? Let us perform an activity to find it out. Activity: take a large, shining metal spoon. Hold its inner surface closer to your face. Can you see your image? Yes, you see an inverted image of yourself. Now, take the spoon away from your face. Do you notice any change in the size of the image? The size of the image diminishes as the spoon is taken away from the face. Now repeat the activity by turning the spoon. What changes in the image do you notice? The image seen is erect. The image diminishes further as the spoon is moved away from the face. The curved surfaces of the spoon can be considered as curved mirrors. The spherical mirror is one of the types of curved mirror that is commonly used. Let us explore more about spherical mirrors. Spherical mirrors.
A curved spherical mirror is actually a segment of the surface of a sphere. Its cross-section is an arc of a circle. It is generally made up of glass. One surface of the glass is silvered so that reflection takes place from the other surface. The mirror in which the outer surface is silvered so that reflection of light takes place from the inner or the concave surface is called a concave mirror. A concave mirror is also called as converging mirror. On the other hand, a mirror in which the inner surface is silvered so that the reflection of light takes place from the outer or convex surface is called a convex mirror. A convex mirror is also called as diverging mirror. Before we see how reflection takes place in these mirrors, we should get familiar with certain terms related to spherical mirrors.
Terms related to spherical mirrors. Center of curvature, abbreviated as C. The center of curvature of a spherical mirror is the center of the sphere of which the given mirror can be considered as a part. Radius of curvature, abbreviated as R. Radius of curvature of a spherical mirror is the radius of the sphere of which the given mirror can be considered as a part. Pole, abbreviated as P. The center point of a given mirror is known as the pole. Here, P is the pole. Principal axis. The straight line passing through the pole and center of curvature of the mirror is known as principal axis. Line XY is a principal axis. Focus of concave mirror, abbreviated as F. The light rays parallel to the principal axis falling on a concave mirror converge to a point on the principal axis after reflection. This point is called the focal point or the focus of the concave mirror. Focal length. The distance between the focus F and the pole P is called the focal length of the mirror and is denoted by F. For small-sized spherical mirrors, the focal length F is half of the radius of curvature, R. That is, F is equal to R by 2.
Aperture. The diameter of the reflecting surface of the mirror is known as aperture of the mirror. D is the aperture of the mirror. It represents the size of the mirror. The size of the aperture determines the sharpness of image. Smaller the aperture, sharper will be the image.
Having learnt about the terms related to spherical mirrors, let us now proceed to understand the concept of convergence and divergence of light by concave and convex mirror. Concave mirror is a converging mirror. Let us hold a concave mirror facing the sun. Try to focus the reflected sun rays on a piece of paper. Move the paper back and forth until a bright, sharp spot of light is seen. This sharp spot of light is nothing but the image of the sun. The distance between the spot of light and mirror is called the focal length of the mirror. The image is formed because the light rays coming from the sun gets reflected and meet at a point. When light rays meet at a point, it is said to converge. When the sun rays are concentrated at a point on the paper for some time, they can burn the paper due to heating. When the light from a source is to be focused on a small spot, a converging mirror is used. Convex mirror is a diverging mirror. Let us consider a beam of light ray falling on a convex mirror. The rays get reflected at the mirror surface and spread away from each other. This is called divergence of rays. When the rays are extended backwards, they appear to come from a point.
This point is on the principal axis and is called the principal focus of the convex mirror, denoted as F.
When we want to spread light from a source, diverging beam is used. For example, in torches and street lamps, light is spread over a larger area using divergence of light.
Before we learn about the image formation by spherical mirrors, let us learn about the representation of images formed by spherical mirrors using ray diagrams. Representation of images formed by spherical mirrors using ray diagrams. When an object is placed in front of a mirror, an image is formed. If we consider an extended object of finite size, each small portion of the extended object acts as a point source. Hence, an infinite number of rays will originate from these points. So, for the sake of clarity, we use only 2 rays of light starting from the object. Let us understand the rules used for drawing ray diagrams for both concave and convex mirrors. Rules used for drawing ray diagram. Rule 1. In case of a concave mirror, if the incident ray is parallel to the principal axis, then the reflected ray passes through the focus. Here the incident ray makes an angle I with the normal. A normal to the surface of the mirror at any point passes through the center of curvature C. The reflected ray makes angle R equal to I with the normal and passes through the focus. In case of a convex mirror, the incident ray of light parallel to the principal axis appear to diverge from the principal focus F on reflection. Rule 2. In case of a concave mirror, if the incident ray passes through the focus, then the reflected ray will travel parallel to the principal axis. In case of a convex mirror, if the incident ray moves towards the mirror in such a way that its extension passes through the focus, then the reflected ray will travel parallel to the principal axis. In both the cases, the incident ray passing or appearing to pass through the focus makes an angle I with the normal at the mirror surface. The reflected ray makes angle R equal to I with the normal and passes parallel to the principal axis. Rule 3. If the incident ray passes through the center of curvature of a concave mirror or is directed in the direction of the center of curvature of a convex mirror after reflection traces the same path. Here the incident ray strikes normally on the mirror surface. Therefore, reflected ray returns along the same path. Rule 4. A ray of light which is incident at pole P of a concave or a convex mirror is reflected back, making the same angle with the principal axis. Here the incident and the reflected rays follow the laws of reflection at the point P, that is, the point of incidence. Thus, they make equal angles with the principal axis. Image formation by spherical mirrors. Activity. Let us perform an activity to understand the formation of image by concave mirror. Take a concave mirror and try to get an image of a distant object on a white screen. This will give us the approximate focal length of the mirror. Mark the position of the stand such that its pole lies over the line. Draw with a chalk 2 more lines parallel to the previous line such that the distance between any 2 successive lines is equal to the focal length of the mirror. These lines correspond to the positions of the points P, that is pole, F, that is focus, and C, that is center of curvature, respectively. Place a candle far beyond the point C. Place a white screen and move it in front of the mirror till you obtain a sharp, bright image of the candle flame on it. Observe the image carefully.
When the position of the candle between infinity and the center of curvature, the image formed is between focus and center of curvature, the size of the image is diminished and nature of the image is real and inverted. When the candle is placed at the center of curvature, the image is formed at the center of curvature. Image is of same size as that of the object and nature of the image is real and inverted. When the candle is placed between focus F and center of curvature C, The image is formed beyond center of curvature. Image is bigger than the object and the nature of the image is real and inverted. When the candle is placed at the focus F, the image is formed at infinity. Image is highly enlarged and the nature of the image is real and inverted. When the candle is placed between the pole and principal focus F of the lens, then the image is behind the mirror. Image is enlarged and the nature of the image is virtual and erect. Assume that an object AB is placed at infinity. Let us consider three rays coming from the object. One along the principal axis and two parallel rays on either side of the principal axis. The ray traveling along the principal axis is incident normally on the mirror and hence retraces its path. The rays parallel to the principal axis pass through the focus after reflection. The three rays meet at the focus and image is formed at that point. The image is real, inverted, and highly diminished. Let the object AB be placed in front of a concave mirror at a distance more than the radius of the curvature. The ray AM, parallel to the principal axis, passes through the focus F after reflection. The ray AN, passing through the center of curvature C, retraces its path. The intersection of the two reflected rays gives the image of the tip A of the object. Considering rays coming out from different points on the object, the images of these points are obtained. Thus, the image A'(B' is obtained between C and F, which is real, diminished, and inverted. Let the object AB be placed at the center of curvature C. The ray AD, parallel to the principal axis, passes through the focus F. The ray AE, passing through the focus, travels parallel to the principal axis as ray EA'. The two reflected rays intersect at point A'. A real and inverted image A'(B') is obtained at C. The size of the image is the same as that of the object. The object AB is now placed between F and C. The rays AD and AE after reflection intersect in point A'. Inverted image A'(B') is obtained beyond C. This image is real and enlarged. When the object is placed at the focus, the rays AE and AD transverse parallel to each other after reflection. The image of the object is formed at infinity. The image is highly enlarged, real, and inverted. Let the object be placed between the pole P and focus F of the mirror. The ray AE after reflection passes through the center of curvature C. Another ray, say AM, gets reflected along MN. The two reflected rays EC and MN appear to come from point A'. Thus, the image A dash B dash of the object is formed. The image is behind the mirror, virtual, enlarged, and erect. Let us tabulate our observations for the image formation by a concave mirror according to the position of the object, position of the image, size of the image, and nature of the image. When the object is placed at infinity, the image is formed at focus, size of the image is highly diminished, nature of the image is real and inverted. When the position of the object between infinity and the center of curvature, the image formed is between focus and center of curvature, the size of the image is diminished, and nature of the image is real and inverted. When the object is placed at the center of curvature, the image is formed at the center of curvature. Image is of same size as that of the object, and nature of the image is real and inverted. When the object is placed between focus F and center of curvature C, the image is formed beyond center of curvature. Image is bigger than the object, and the nature of the image is real and inverted. When the object is placed at the focus F, the image is formed at infinity. Image is highly enlarged, and the nature of the image is real and inverted. When the object is placed between the pole and principal focus, F, of the lens, then the image is behind the mirror. Image is enlarged, and the nature of the image is virtual and erect. The distance of the image depends upon the distance of the object from the mirror and the focal length of the mirror.
Let us see some of the uses of concave mirrors.
Concave mirrors are used as shaving mirror to see an enlarged image of the face. The makeup mirrors are also made up of concave mirrors. Dentists use concave mirrors fitted in a frame with a long handle to see an enlarged image of the tooth to detect the defect in the tooth easily. Concave mirrors are used as reflectors in headlights of vehicles. The reflectors of torches and searchlights also make use of concave mirrors. Let us perform an activity to understand the formation of image by convex mirror. Make sure that you perform this activity in a dark room. Place a convex mirror of focal length 10 centimeters on a stand. Keep a lighted candle on one side of the mirror at any distance, say 20 centimeters from the mirror. Place a screen in front of the mirror. Now, move the screen forward and backward, and try to obtain the image of the candle flame on the screen. You will observe that there is no image of the candle flame formed on the screen. But if you look into the mirror by adjusting your eye, a small image of the candle and its flame is seen. Since you can see the image of the candle and its flame only when you looked into the mirror, the image observed is virtual. The image formed has the flame on the same side as that of the candle. Thus, the image is erect. But if we compare the size of the image with the candle, we find that the size of the image is small, that is, the image is diminished. Thus, we can conclude that the image formed by the convex mirror is always virtual, erect, and smaller in size independent of the distance between the object and mirror.
Let us consider two positions of an object to study its ray diagram. Let the object, that is, the pencil, AB, be placed in front of the convex mirror anywhere between the pole and infinity. Let us consider a ray AD traveling parallel to the principal axis. It gets reflected as a ray DM. According to the rules, the ray appears to come from focus F. The other ray AG traveling towards the center of curvature C gets reflected along the incident path as ray GA. The two reflected rays DM and GA do not actually meet at a point but appear to meet at point A' behind the mirror. Thus, A' is the virtual image of the point A. Hence, A', B' is the virtual image of the object AB. The image is situated between the pole and the focus. The image is virtual, upright, and diminished. If the object is situated at infinity, the rays coming from the object are such that they are parallel to the principal axis. The rays diverge on reflection and a virtual, highly diminished image is seen at the focus F. Hence, for all the positions of an object in front of a convex mirror, the image formed is on the other side of the mirror between focus F and pole P. Let us tabulate our observations for the image formation by a convex mirror according to the position of the object, position of the image, size of the image, and nature of the image. When the object is placed anywhere between the pole P and infinity, then the image is formed behind the mirror between P and F. The image is diminished and nature of the image is virtual and erect. When the object is placed at infinity, then the image is formed behind the mirror at the focus F. The image is highly diminished and nature of the image is virtual and erect. Having learnt about the formation of image in plane and spherical mirrors, can you tell which mirror will give you a full-size image of a large object? Well, to know this, let us perform an activity. Activity: try to get a full-sized image of a distant tree in a plane mirror. Do you get the full-size image of the tree? No. In the plane mirror, you will not get the full-sized image. Let us take another plane mirror of different size and try to get a full-size image of the tree. Do you succeed this time? No. Now, try to get the full-sized image of a tree in a concave mirror. Do you get the full-size image of the tree?
The size of the image is diminished and it is inverted.
Repeat the same steps with a convex mirror. This time you will be successful. It is because the convex mirror has a greater field of view. Let us study some more uses of convex mirrors.
Uses of convex mirror. Convex mirror always produces a smaller, virtual and erect image of an object. Hence, it is used as a side view mirrors in vehicles. it forms images of the vehicles that are spread over a relatively larger area, providing a wider field view. Also, convex mirrors are used for security purpose in shops, malls, etc.
Sign convention for reflection by spherical mirrors.
We have seen that images are formed at different distances from a mirror depending on the distance of the object from the mirror. The distances are measured using new sign convention. According to it, the pole P of the mirror is taken as the origin. The principal axis is taken as x-axis, x dash of the coordinate system. The conventions are: the object is always placed to the left of the mirror. This means light from the object falls on the mirror from the left-hand side. All distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin, that is along positive x-axis, are taken as positive, while the distances measured to the left of the origin, that is along the negative x-axis, are taken as negative. Distances measured perpendicular to and above the principal axis are taken as positive. Distances measured perpendicular to and below the principal axis are taken as negative. The sign conventions are applied to obtain mirror formula.
Let us study more about the mirror formula. Mirror formula and magnification.
Mirror formula. The distance of the object from the pole of the mirror is called the object distance. It is designated by letter U. The distance of the image from the pole of the mirror is called the image distance. It is designated by letter V. The distance between the pole and the principal focus is designated by letter F. The relation between the object distance, image distance, and the focal length of the mirror is called mirror formula. It is given as 1 divided by V plus 1 divided by U is equal to 1 divided by F. This formula is valid in all situations for all spherical mirrors for all positions of the object. We have seen how object distance, image distance, and the focal length are connected. Now, let us study more about the relation between the object and image sizes. Magnification. We have seen that the size of an image is different for different object distances. The image is magnified in some cases and diminished in some cases. A term magnification is defined as the ratio of the height of the image to the height of the object. Thus, the magnification by spherical mirror is given by magnification is equal to height of the image divided by height of the object. Magnification gives the relative extent to which the image of an object is magnified with respect to the object size. Magnification is usually denoted by the letter M. If h is the height of the object and h dash is the height of the image, then the magnification M produced by a spherical mirror is given by M is equal to H dash divided by H. The object is usually placed above the principal axis, hence is taken to be positive. The height of image should be taken as positive for virtual images and negative for real images. The magnification M is also related to the object distance U and image distance V. It can be expressed as M is equal to H dash divided by H equal to negative V divided by U. A negative sign in the value of the magnification indicates that the image is real. A positive sign in the value of the magnification indicates that the image is virtual. Numerical problems. 1. An object 3 cm in size is placed at 20 cm in front of a concave mirror of focal length 12 cm. At what distance from the mirror should a screen be placed in order to obtain a sharp image? Also find the nature and size of the image. Solution. Let us first write the given data using sign convention. Object size H is equal to 3 cm. As a convention, the object is always placed left to the mirror. Hence, according to sign convention, the distance of the object is taken as negative. Object is placed at 20 cm in front of the concave mirror. Therefore, object distance U is equal to minus 20 cm. The focal length of a concave mirror is negative. The focal length of a given concave mirror is 12 cm. Therefore, focal length F is equal to minus 12 cm. We have to find the image distance V and the image size H dash. Let us use the mirror formula. 1 divided by V plus 1 divided by U is equal to 1 divided by F, which can be written as 1 divided by V is equal to 1 divided by F minus 1 divided by U. Let us substitute the given values of F and U. 1 divided by V is equal to 1 divided by minus 12 minus 1 divided by minus 20 is equal to minus 5 plus 3 divided by 60, which is equal to minus 2 divided by 60. Therefore, V is equal to minus 30 cm. Hence, the screen should be placed at a distance of 30 cm in front of the mirror. As the image can be obtained on the screen, it is a real and inverted image. Now the magnification M is given by M is equal to H dash divided by H, which is equal to minus V divided by U. Therefore, H dash is equal to minus V divided by U multiplied by H. Substituting given values of U, V and H, we have H dash is equal to minus 30 multiplied by 3 divided by minus 20. which is equal to 90 divided by minus 20, which is equal to minus 4.5. Hence, the height of the image is 4.5 centimeter. Now the magnification M is equal to minus 4.5 divided by 3, which is equal to minus 1.5. Hence the image is real, inverted and enlarged.
2. An object is placed at a distance of 10 centimeters from a convex mirror of focal length 15 centimeters. Find the position and nature of the image. Solution. Let us first write the given data using new sign convention. As a convention, the object is always placed to the left side of the mirror. Hence, according to sign convention, the distance of the object is taken as negative. Object is placed at 10 centimeters in front of the convex mirror. Therefore, object distance U is equal to minus 10 centimeters. The focal length of a convex mirror is always positive. The focal length of the given convex mirror is 15 centimeters. Therefore, focal length F is equal to 15 centimeters. We have to find out position, that is, V of the image. Let us use the mirror formula. 1 upon F is equal to 1 upon U plus 1 upon V, which can be written as 1 upon V is equal to 1 upon F minus 1 upon U. Substituting the given values, we get 1 upon V is equal to 1 upon 15 minus 1 upon minus 10, which is equal to 1 upon 15 plus 1 upon 10, which is equal to 2 plus 3 the whole divided by 30, which equals to 5 by 30. Therefore, 1 upon V is equal to 1 upon 6. Therefore, V is equal to 6 centimeters. Hence, the image formed will be 6 centimeters away from the pole of the mirror. The image formed by a convex mirror is always erect and virtual and is formed behind the mirror. Refraction of light.
Opaque objects reflect most of the light that is incident on them. But what happens when light passes through transparent substances such as water or glass? In our day-to-day life, we come across many such optical phenomena. For example, a glass slab placed on a book, a pencil dipped partly in water, and a swimming pool. What do you notice in each of these examples? The letters below the glass slab appears to be raised. The pencil appears broken at the water surface, whereas the swimming pool appears shallower than its actual depth.
Let us understand this by performing some activities.
Take some water in a glass container. Now take a heavy rubber ball and immerse it slowly in the water. Observe the ball from one side of the container. What do you observe? Do you notice any change in the size of the ball? Yes, the size of the ball varies. Now take a beaker filled with water. Take a pencil and place it vertically in water such that some part of the pencil is immersed in water. Look at the pencil carefully. You will observe that the thickness of the pencil inside the water appears to be more than the thickness of the part of the pencil that is outside the water. Place the pencil obliquely in the beaker. What do you observe? You will observe that the pencil appears broken at the surface of water where the light rays emerge from water and enter the air. This happens because the light rays traveling from one medium to another change their direction of propagation. This phenomena of light is called as refraction of light.
Activity.
Place a coin at the bottom of a glass jar containing water. Now tilt the jar suitably. When viewed from a suitable angle, the coin appears to be floating. Can you explain why? When you place a coin at the bottom of a glass jar, the rays of light begin to emerge from the coin. Initially, they are in the water medium. When the rays emerge out of the water, they travel in the air medium. On entering the air medium, they change their direction. Let us consider ray AB incident on the interface of water and air at an angle of incidence I. The ray deviates away from the normal to the interface and emerges as ray BC. The coin appears to be raised. When the jar is tilted, the ray AB is incident at higher angle of incidence on the interface and gets deviated from the more normal and travels along path BD. The coin appears to rise further. If the jar is further tilted at a suitable angle, called critical angle of incidence, the ray AB gets deviated away from the normal and grazes just along the surface of water, and the coin is felt to be floating on the surface. We have seen the effects of refraction of light when it travels from one medium to another.
Let us understand the concept of refraction in detail.
Concept of refraction of light. Light travels along a straight line in a transparent medium. The velocity of light is maximum in vacuum and is equal to 3 multiplied by 10 raised to 8 meter per second. It is marginally less in air. It has been found that light rays propagate with different speed in different media. Therefore, the direction of propagation of light rays changes when it travels from one medium to another. The phenomena of change in the direction of light rays when it passes from one transparent medium to another is called refraction. Let us understand the change in the direction of path of light rays due to refraction with the help of an activity.
Refraction through a rectangular glass slab. Let us perform an activity to trace the path of light through a glass slab.
Fix a white paper on a drawing board. Place a rectangular glass slab on it. Mark the boundary of the slab as ABCD. Fix 2 pins P1 and P2 about 5 cm away on the side AB of the glass slab in such a way that the pins are vertical and the line passing through P1 and P2 meet the glass slab obliquely. Observe these pins through the glass slab from the opposite side DC. Now fix 2 pins P3 and P4 in such a way that they cover the images of the first two pins, P1 and P2 respectively. What do you notice? You will notice that all the 4 pins appear to be in the same straight line. Remove the glass slab and the pins and mark the positions of the pins. Draw a straight line joining P1 and P2 and produce it to meet the line AB at point Q. Let PQ be the incident ray. Similarly, draw a line joining P3 and P4 and produce it to meet the line DC at point R. Let RS be the emergent ray. Join the points Q and R. QR is the refracted ray. Thus, PQRS is the path of the ray of light. In the absence of the glass slab, the light would have travelled along the path PQT. What can infer from the direction of the emergent ray and the incident ray? The emergent ray and the incident ray are parallel to each other. Can you tell how many times the light rays encounter a change in the medium? Light rays encounter a change in the medium twice. That is, they are refracted 2 times. First at point Q and then at point R. The ray of light enters the glass from air at point Q. It gets refracted and travels along QR. Again at point R, when the ray of light passes from the glass to air, there is a change in the direction of propagation due to refraction. The ray of light shifts slightly to the left side. Can you explain why? Well, the ray of light is deviated towards the normal to the surface AB at point Q. The ray of light travels along a straight line QR and gets deviated away from the normal to the surface CD at R through the same angle. The magnitude of angle of deviation depends upon the relative property of the two media. This property is known as the refractive index.
Light rays on going from one medium to another follow the laws of refraction. Let us study the laws of refraction in detail.
Laws of refraction. Consider a ray of light PQ incident obliquely at point Q on the surface AB of a glass slab. Since air and glass are two transparent media and glass is more dense than air, the ray of light gets deviated towards the normal and travels along the path QR. Here, NQN dash is the normal at the point of incidence. The angle PQN is the angle of incidence I and angle N dash QR is the angle of refraction R, and here I is greater than R. The refraction takes place according to the laws of refraction, which are the incident ray, the refracted ray and the normal at the point of incidence all lie in the same plane. For a given pair of media, the ratio of sine of angle of incidence to the sine of angle of refraction is constant. That is, sine I upon sine R is equal to constant. This constant is called as the refractive index of the second medium with respect to the first medium. It is denoted by N. Let us perform an activity to understand the concept of refractive index.
The refractive index.
Take a drawing board and fix a sheet of white paper on it using drawing pins. place a plastic slab in the center and draw the outline of the slab using a pencil and label it as ABCD. Fix 2 pins P1 and P2 on the side of AB of the plastic slab so that the pins are vertical and the line passing through P1 and P2 meet the glass slab obliquely. See the pins from side CD of the plastic slab. Fix 2 pins P3 and P4 in such a way that they cover the images of the first 2 pins P1 and P2 respectively. Now all 4 pins appear to be in the same straight line. Remove the plastic slab and the pins. Mark the positions of the pins. Draw the line PQ through points of impression of pins P1 and P2. PQ is the incident ray. Similarly, draw a straight line joining points P3 and P4 and produce it to meet the line DC at point R. RS is then the emergent ray. If we compare the refraction of light through a transparent slab with that through a plastic slab, we find that in both the cases light refracts in a similar way. The light gets deviated towards the normal when it enters from air to glass or from air to plastic. However, the deviation is more in case of glass than that in plastic. Again, when the light enters the air either from glass or from plastic, it gets deviated away from the normal. Here, the deviation is more for the light entering air from the glass than that from plastic. This shows that the deviation of the ray of light is different for different substances. It depends on a property called refractive index. Refractive index of a medium relative to another medium. The refractive index depends upon the relative speed of propagation of light in different media. Let V1 be the velocity of the light in medium 1 and V2 be the velocity in medium 2. Therefore, the refractive index of medium 2 with respect to medium 1 is given by the ratio of the magnitude of velocity of light in medium 1 to that in medium 2. It is represented as 1n2. 1n2 is equal to velocity of light in medium 1 upon the velocity of light in medium 2. That is, 1n2 is equal to V1 upon V2. Similarly, the refractive index of medium 1 with respect to the medium 2 is given by 2n1 is equal to V2 upon V1. The refractive index is a pure number as it is the ratio of two velocities. Refractive index of a medium by convention is stated with respect to vacuum and is also called the absolute refractive index of the medium. Let us understand this concept in detail. Absolute refractive index of a medium. If light traveling through vacuum is incident on a transparent medium, then the ratio of the velocity of light in vacuum to the velocity of light in a particular medium is called as absolute refractive index of that medium. Absolute refractive index of glass is defined as the ratio of the velocity of light in vacuum to the velocity of light in glass and is represented as Ng. If Vg is the velocity of the light in glass and c is the velocity of light in vacuum, then Ng is equal to c upon Vg. The absolute refractive index of a medium is simply called its refractive index. The ability of a medium to refract light is expressed in terms of its optical density. A medium with larger refractive index is termed as optically denser medium, and the medium with lower refractive index is termed as optically rarer medium. The speed of light is greater in a rarer medium as compared to a denser medium. As a result, a ray of light traveling from a rarer medium to a denser medium slows down and bends towards the normal. Let us consider a ray of light traveling from air to glass. Let I be the angle of incidence. Here, the refractive index of glass is greater than the refractive index of air. We know that the greater the value of refractive index, more is the bending of the refracted ray towards the normal. Let R be the angle of refraction. In this case, the angle of incidence is greater than the angle of refraction. For a ray traveling from denser medium to the rarer medium, the speed of light increases and the ray bends away from the normal. Here, the angle of refraction is greater than the angle of incidence. What happens when a ray is incident normally on the interface between the two media? The ray which is incident normally on the interface between the two different media propagates undeviated from one medium to another. Consider a ray of light traveling from a rarer to denser or denser to rarer medium. Here, angle of incidence is 0. Therefore, the angle of emergence is also 0. The absolute refractive index is a very important optical characteristics of a transparent medium. Absolute refractive index of some material media. Refractive index for different media is different. The refractive index of some material media are given in a tabular form. Which of the two, crown glass and water, is optically more denser? The refractive index of crown glass is 1.52, while the refractive index of water is 1.33. Hence, crown glass is optically denser than water. It is not necessary that an optically denser medium possesses a greater mass density. For example, kerosene is found to be optically denser than water as its refractive index is more than that of water. However, the mass density of kerosene is 0.817, which is much less than that of water, which is 1. Hence, although the optical density of kerosene is higher than that of water, its mass density is found to be lower.
Having studied about the refraction of light, let us now study the refraction of light by spherical lenses. Refraction by spherical lenses.
Have you seen the night sky through a telescope? How beautiful and big our moon is seen through the telescope. We can see many details on its surface. Do you know lenses are used in the telescope? Lenses are used in many optical instruments. Can you name the instruments where you have seen a lens? Binoculars, microscope are the instruments which use lenses. A magnifying glass is a very common instrument in every household. This is also a kind of a lens. The spectacles used by many people to correct their eyesight are also lenses. We all have lens in our eyes. Hence, our eye is a natural optical device. A lens can be defined as a transparent material bound by two surfaces, out of which at least one surface is spherical. A lens can have two spherical surfaces bulging outwards. Such a lens is called a double convex lens or simply a convex lens. It is thicker at the middle than at the edges. A beam of light incident on the convex lens is converged. Hence it is also called as a converging lens. A lens having two spherical surfaces curved inwards is called a double concave lens or simply a concave lens. It is thicker at the edges than at the middle. A light beam incident on it is diverged. Therefore, such lenses are called as diverging lenses.
Before we learn more about the lenses, let us get familiar with the terms related to spherical lenses.
Concepts related to lenses. Both convex and concave lenses have two spherical surfaces. Each of these surfaces form a part of a sphere. Let us define some concepts related to lenses. Center of curvature C. The spherical surface of the lens can be imagined to form a part of a sphere. The center of this sphere is called as center of curvature. It is usually represented by the letter C. There are two surfaces, hence there are two center of curvatures, C1 and C2, corresponding to two surfaces. Principal axis. The line passing the two centers of curvature is the principal axis of the lens. That is the line joining C1, C2 is the principal axis of the lens. Optical center, O. The central point of the lens on the principal axis is called as its optical center. A ray passing through the optical center of a lens passes without undergoing any deviation. Principal focus of a convex lens, F. To understand what is principal focus of a convex lens, consider several rays of lights parallel to the principal axis are incident on one of the surface of a convex lens. The rays get converged at a point on the principal axis after passing through the lens. This point is called as principal focus of the convex lens. If the parallel rays are incident on the other surface of the lens, the rays will converge on a point on the opposite side. Thus, a lens has two principal foci.
Principal focus of a concave lens, F. In case of a concave lens, the rays of light incident parallel to the principal axis diverge from each other after undergoing refraction at the lens. These rays appear to be coming from a point on the principal axis. This point is known as the principal focus of the concave lens. A concave lens also has two principal foci. They are termed as f1 and f2. Aperture. The effective diameter of the circular outline of a spherical lens is called the aperture. D is the aperture of the lens. Aperture is one of the important factor over which the quality of image depends. The size of aperture determines the sharpness of the image. Smaller the aperture, sharper the image will be. Focal length f. The distance of principal focus from optical center of the lens is called focal length. What happens when parallel rays of light are incident on a lens? Let us understand this by performing an activity.
Let us perform an activity to understand what happens when a parallel beam of light falls on a convex lens. Take a convex lens and hold it in such a way that its one side faces the sun and the other side faces a piece of paper. Adjust the distance between the paper and the lens such that you get a sharp and bright point image of the sun on the paper. This distance between the paper and lens is equal to the focal length of the lens. Hold the lens in the same position for some time. You will observe that the paper begins to burn at the point where the image of the sun was formed. Why does this happen? Well, this is because the parallel rays of light coming from the sun converge at a point by the lens. The higher concentration of the light rays at that point causes the heating. As the paper at the point of image gets heated too much, it results into the burning. Thus, we can infer that when parallel rays of light pass through a convex lens, the refracted rays converge at a point.
Before we learn the image formation by lenses, let us perform an activity to find the approximate focal length of a convex lens.
Take a lens stand, a screen, and a distant object. A tree seen through a window can serve as the distant object. Place the screen on a table placed close to an open window facing a tree. Place the lens on the lens stand. Now, place the stand in between the screen and the distant object, that is, the tree seen through the window. Let us move the lens stand towards or away from the screen. Do you get a well-defined image on the screen? At particular distance of the lens from the screen, the image of the tree obtained on the screen is well defined. Can you guess at which point do you get the well-defined image? It is the focal length of the lens. The rays falling on the lens coming from a distant object converge after going through the lens. Hence, the distance between the screen and the lens is the approximate focal length of the lens. The position of the image depends on the position of the object relative to the lens. Let us study position, relative size, and the nature of images formed by a lens.
Image formation by lenses. Image formation by convex lenses. Let us perform an activity to understand the image formation by a convex lens.
First, let us find the approximate focal length of the convex lens. Obtain a well-defined image of a distant object on the screen. Measure the distance between the screen and the lens. It is the approximate focal length of the lens. Let us call it to be f. Draw a horizontal line on the table. Mark the center. Place the lens stand with lens at the center mark. Mark points at distances f and 2f on both the sides of the lens. Label these marks as 2f1, f1, f2 and 2f2 respectively. Take a burning candle. Place the burning candle at different positions relative to the lens. Place the screen on the opposite side of the lens. Place the object far beyond 2f1 to the left. Here, the object, that is the burning candle, is placed at a very large distance from the lens. Obtain a clear and sharp image of the candle on the screen by adjusting the screen distance from the lens. The sharp image is obtained at focus f2. The image is highly diminished or point-sized. As the image is obtained on the screen, the nature of the image is real and inverted. Object just behind 2f1. Place the burning candle just behind 2f1. Adjust the screen distance from the lens. The sharp image of the candle is obtained between f2 and 2f2. The image is diminished. The nature of the image is real and inverted. Object at 2f1. Place the burning candle at 2f1. Adjust the screen distance from the lens. The sharp image of the candle is obtained at 2f2. The image is of same size that of the object. The nature of the image is real and inverted. Object between f1 and 2f1. Now place the candle between f1 and 2f1. Move the screen and obtain the well-defined image of the candle. The position of the screen is beyond 2f2. The image is enlarged, real and inverted. Object at focus f1. Now place the candle at focus f1. Move the screen to obtain a well-defined image on the screen. As image is formed at infinity, it cannot be obtained on the screen. Object between focus f1 and optical center O. Place the candle between focus f1 and optical center O. Try to locate the image on the screen kept on the other side of the lens. It is not possible to obtain the image of the candle on the screen. You can view an enlarged and erect image of the candle on the same side of the lens. It is a virtual image. Let us tabulate our observations. Characteristics of images formed by a convex lens. Let us tabulate the information of formation of images by a convex lens when object is placed at different positions relative to the lens. Let us make columns with headings: position of the object, position of the image, relative size of the image, and nature of the image. When the position of the object is at infinity, the image is formed at focus f2. The image is highly diminished or point-sized, and nature of the image is real and inverted. When object is placed beyond 2f1, The image is formed between f2 and 2f2. The image is diminished and nature of the image is real and inverted. When object is placed at 2f1, the image is formed at 2f2. The image is of same size as that of the object and nature of the image is real and inverted. When object is between f1 and 2f1, the image is formed beyond 2f2. The image is enlarged and nature of the image is real and inverted. When object is placed at focus f1, the image is formed at infinity. The image is highly enlarged and the nature of the image is real and inverted. When object is placed between focus f1 and optical center O, the image is enlarged and the nature of the image is virtual and erect.
Uses of convex lenses. It is used as a magnifying glass by watch repairers, palm readers, jewelry designers, etc. A convex lens is used to make a simple camera.
Image formation by concave lenses. Let us perform an activity to understand the image formation by a concave lens. Place a concave lens on a stand. Keep a lighted candle on one side of the lens. Place a screen on the other side of the lens. Now, move the screen forward and backward and try to obtain the image of the candle flame on the screen. You will observe that there is no image of the candle flame formed on the screen. But if you look through the lens by adjusting your eye behind the lens, a small image of the candle and its flame is seen inside the lens. Now, move the candle away from the lens and observe the size, nature, and position of the image. What do you observe? Well, you will observe that the size of the image always remains smaller than the size of the candle. Also, the image remains virtual and erect in nature. Let us consider two positions of the object to study its ray diagram. Let the object, that is, the candle, be AB, placed in front of the concave lens anywhere between the optical center and infinity. Let us consider a ray AD traveling parallel to the principal axis. It gets refracted as a ray DD' so as to appear to come from the focus F1. The ray AO traveling towards the optical center O passes undeviated after refraction as OO'. The two rays DD' and OO' do not actually meet at a point but appear to meet at a point A', which is the virtual image of the point A. Hence, A', B' is the virtual image of the object AB, which is erect and diminished. If the object is placed at infinity, the rays coming from the object are such that they are parallel to the principal axis of the concave lens. The rays appear to diverge from the focus F1. Thus, a virtual, erect, and highly diminished point-size image is formed. Characteristics of image formed by a concave lens. Let us tabulate the information of formation of images by a concave lens when object is placed at different positions relative to the lens. When the object is placed between the infinity and the optical center O of the lens. The image is formed between the focus f1 and optical center O. The size of the image is diminished. The nature of the image is virtual and erect. When the object is placed at infinity, the image is formed at the focus f1. The image formed is highly diminished, and the nature of the image is virtual and erect.
Uses of concave lenses. Concave lenses are used in spectacles to correct the defect of vision. Concave lenses are used in certain types of telescopes. Concave lenses are used as a wide-angle spy hole indoors to see the image of a person standing outside the door.
Image formation in lenses using ray diagrams. The information about position, relative size and nature of the image formed by lenses can also be obtained by drawing ray diagrams. The ray diagrams are drawn following certain rules. Let us see what are the rules followed for drawing ray diagrams for the formation of images by convex and concave lens. Rules used for obtaining images by convex and concave lens. Rule 1. If a ray parallel to the principal axis is incident on a convex lens, then after refraction it passes through the focus on the other side of the lens. In case of a concave lens, the ray after refraction appears to diverge from the principal focus, which is located at the same side of the lens. Rule 2. In case of both the lenses, a ray of light passing through the optical center of a lens will emerge without any deviation. Rule 3. A ray of light passing through the principal focus of a convex lens emerges parallel to the principal axis after refraction. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis. Let us use these rules and draw ray diagrams for the image formation in a convex lens for different positions of an object.
Ray diagrams for the image formation in a convex lens for different positions of an object. Let us consider an object AB placed above the principal axis of a convex lens. Let us draw ray diagrams for different positions of the object. Position of the object at infinity. As the object is placed at infinity, the rays coming from the object are parallel to the principal axis. The parallel rays, after passing through the lens, converge at the focal point on the other side. Hence, the image is formed at f2. The image is highly diminished, real, and inverted. Object beyond 2f1. Let the object be placed beyond 2f1. Let us consider two rays AC parallel to the principal axis and the ray AO passing through the optical center O of the lens. The ray AC passes through focus f2 and the ray AO passes through the optical center without any deviation. Thus, the image A'(B') is formed between f2 and 2f2. The image is diminished, real, and inverted. Object at 2f1. The ray AC passes through F2, while the ray AO passes through the optical center without any deviation. Hence, the image A-B- is formed at 2F2. The image is of the same size as that of the object, real and inverted. Object between F1 and 2F1. The ray AC passes through F2, while the ray AO passes through the optical center without any deviation. Hence, the image A-B- is formed beyond 2F2. The image is enlarged, real and inverted. Object at focus F1. The ray AC passes through F2, while the ray AO passes through the optical center without any deviation. The two rays travel parallel to each other after passing through the lens. The rays will meet at infinity. Hence, the image will be formed at infinity, which is highly magnified, real and inverted. Object between F1 and optical center O. The rays AC and AO diverge after passing through the lens. They appear to come out of a point on the same side of the lens as the object. This gives rise to a virtual, enlarged and erect image of the object.
Ray diagrams for the image formation in a concave lens for different positions of an object. Let us consider an object AB placed on the principal axis of a concave lens. Let us draw ray diagrams for two positions of the object. Object at infinity. When the object is placed at infinity, the rays coming from the object are parallel to the principal axis. The parallel rays, after passing through the lens, diverge on the other side of the lens. When seen from the other side, the rays of light seem to originate from the point
F1.
Hence, the image is formed at
F1.
2. Object between infinity and the optical center O of the lens. When the object is placed between infinity and the optical center O of the lens, the image is formed between focus
F1
and optical center. In spherical mirrors, we used mirror formula with certain sign conventions to find position, size and type of the image formed. Similarly, for lenses we have sign conventions and lens formula. Let us explore more about it. Sign convention for spherical lenses.
The focal length of convex lens is positive and that of concave lens is negative. Optical center of the lens is taken as origin and principal axis is taken as x-axis. The sign conventions used for an object distance u, image distance v, object height h and image height h dash are same as those used for spherical mirrors.
Lens formula and magnification.
Lens formula. The lens formula gives the relationship between object distance u, image distance v and the focal length f. Here, distances are measured from optical center using proper sign conventions. The lens formula is given as 1 divided by V minus 1 divided by U is equal to 1 divided by F. The lens formula is general and is valid in all situations for any spherical lens. Now, let us define the term magnification by a lens. Magnification by a lens. Magnification produced by a lens is defined as the ratio of the height of the image to the height of the object. Magnification is equal to height of the image divided by height of the object. Magnification gives the relative extent to which the image of an object is magnified with respect to the object size. Magnification is usually denoted by the letter M. If h is the height of the object and h dash is the height of the image, then the magnification M produced by a lens is given by M is equal to h dash divided by h. The magnification M is also related to the object distance U and image distance V. It can be expressed as M is equal to h dash divided by h, which is equal to V divided by U. A negative sign in the value of the magnification indicates that the image is real. A positive sign in the value of the magnification indicates that the image is virtual.
Let us solve a numerical problem to find the magnification produced by a lens.
Numerical problems. 1. A 3 cm tall object is placed perpendicular to principal axis of a convex lens of focal length 15 cm. The distance of the object from the lens is 18 cm. Find the nature, position, and size of the image. Also, find its magnification. Solution. Let us first write the given data. Height of the object, h, is equal to 3 cm. Focal length, f, is equal to 15 cm. The given lens is convex. Hence, the focal length is positive. Object distance u is equal to minus 18 cm. The negative sign is used as the object is placed on the left side of the lens. We want to find the image distance v and the size of the image h dash and its nature. According to lens formula, we have 1 divided by v minus 1 divided by u is equal to 1 divided by f. Therefore, 1 divided by v is equal to 1 divided by u plus 1 divided by f. Substituting the given values of u and f, we have 1 divided by v is equal to 1 divided by minus 18 plus 1 divided by 15. 1 divided by v is equal to minus 5 plus 6 divided by 90. 1 divided by v is equal to 1 divided by 90. Hence, v is equal to 90 centimeter. The positive sign of the image distance indicates that the image is formed on the other side, that is, on the right side of the lens at a distance of 90 centimeter from the optical center. Now, to find the height of the image h dash, let us use the formula of magnification. It is given by m is equal to h dash divided by h is equal to v divided by u. Hence, h dash is equal to v divided by u multiplied by h, which is equal to 90 divided by minus 18 multiplied by 3, is equal to minus 15 centimeter. The height of the image is 15 centimeter. It is negative, hence the image is inverted. It is formed below the principal axis. Let us find the magnification m using m is equal to h dash divided by h, or m is equal to v divided by u. Therefore, m is equal to minus 15 divided by 3. Therefore, m is equal to minus 5. The negative sign of magnification shows that the image is real. Hence, a magnified, real and inverted image of the height 15 centimeter is formed at a distance of 90 centimeter on the other side of the lens.
Power of a lens.
Power of a lens. We have seen that convex lens is a converging lens, while a concave lens is a diverging lens. A convex lens of short focal length bends the light rays through large angles by focusing them closer to the optical center. A convex lens of larger focal length bends the light through smaller angles and focuses them away from the optical center. Hence, the ability of a lens to converge or diverge light rays depends on its focal length. Smaller the focal length, larger the convergence. The degree of convergence of light rays by a convex lens is expressed in terms of power of the lens. The power of a lens is defined as the reciprocal of its focal length. It is represented by the letter P. Hence, the power P of a lens of a focal length f is given by P is equal to 1 divided by f. The SI unit of power is diopter. It is denoted by letter D. The focal length is expressed in meters. Hence, if the focal length of a lens is 1 meter, then the power of the lens is equal to 1 diopter. That is, 1 diopter is equal to 1 divided by 1 meter. According to sign conventions, the focal length of a convex lens is taken positive and that of concave lens negative. Therefore, the power of a convex lens is positive and the power of a concave lens is negative. You must have seen opticians mentioning power of lenses used in spectacles in diopters. A lens of power plus 2.0 D means a convex lens of focal length 0.5 meter.
Let us solve a numerical problem.
1. Calculate the focal length of a corrective lens having power plus 2.5 D. Solution. Let us first write the given data. Power of lens P is equal to plus 2.5 diopter. We know that the power of a lens is related to the focal length of the lens by P is equal to 1 divided by F. Therefore, F is equal to 1 divided by P. Substituting the given value of the power, we have F is equal to 1 divided by 2.5. F is equal to 0.4 meter, or F is equal to 40 centimeter. Hence, the focal length of the convex lens having a power plus 2.5 D is 0.4 meter, or 40 centimeter.